durable and as easy to use as disk-based storage systems. Now, so what I'm talking about today is essentially how we provide durability and availability in RAMCloud. And to provide durability, we use a pervasive log structure, even for data in RAM that uses inexpensive disks for replication, but it still eliminates synchronous writes from the update path for high performance. Since data is stored on disk, this means when a node crashes in RAMCloud, our data is unavailable. So we use our fast crash recovery system to reconstitute the RAM of a crash host in just 1 to 2 seconds and restore full performance to the cluster. Right now, with our small 60-node TUS cluster, we're able to recover 35 gigabytes of RAM from a crash host in just 1.6 seconds. And to do this, we have to use all of the hosts in the entire system, balancing work across them and avoiding centralized bottlenecks. So this is what a typical RAMCloud deployment might look like. We have several thousand storage nodes with running our software, servicing 100,000 application servers or more that are linked against a small RAMCloud client library. And this client library generates RPCs that traverse the data center network. And we think in the future, the data center networks with 10 gigabit Ethernet will be able to provide round-trip times of a few microseconds across the data center. So these go directly to RAMCloud storage nodes. And these storage nodes provide two distinct services. First, the master service exports the RAM of the host and organizes as a key value interface to clients. And each key in RAMCloud is assigned to just one master, and all read and write requests are serviced by that master and from its RAM. And then secondly, there's a backup service which accepts data from other masters in the cluster in the case that they might crash and has it stored durably for recovery. And finally, we have a coordinator which verifies host failures, manages cluster membership, and initiates recoveries. In practice, it tends to be lightly loaded even during recovery because recovery is relatively autonomous. So we want to provide durability and availability, but RAM provides some particularly stringent requirements. We want to involve disks, but we want RAM-like performance. And RAM's expensive, so we don't want additional hardware or energy consumption costs. So one approach you might think of is to triplicate each object, say in the RAM of 3 different masters, but that would triple hardware costs, triple energy consumption, and we'd still lose our data on power failures. So RAMCloud's approach instead is to just keep one copy of each object in one host's RAM and service all operations from that copy. So that means we get RAM performance, and then we just keep cheap backup copies on disks, which are cheap compared to the rest of the cost of the system. But because we've reintroduced disks, we've brought some problems back along with them. First, synchronous disk writes are too slow for updates. We'll lose our RAM-like performance for updates. So we have a pervasive log structure, which I'll describe in a moment, that sidesteps this problem. And second, because our data is stored on disk, this means that it's unavailable when a host crashes. So remember, what we want to do here is recover an entire host in just 1 to 2 seconds. So we think if we can do it this quickly, then applications won't even really notice. They'll simply see crashes in our system as performance hiccups. So how do we do durability in RAMCloud? So here's a master servicing a write request. And to do it, it simply takes the update, the object update that the client's providing, and stores it in memory. And then 3 other hosts in the system are acting as backups on behalf of this master, and so it broadcasts that update to those backups. And the backups buffer it in RAM. And once this has happened, the master returns the client, notifying it that its data is durable even if hosts fail. Now, there's no synchronous disk write here. The data is simply buffered in the RAM of the backups. And over time, the backups are accumulating more and more updates, and they flush these updates in bulk out in the background to disks. So they achieve high disk bandwidth doing this. But it also means we need to guarantee durability of these buffers in case of a power loss event. So there are a couple of ways to do this. One approach is to simply rely on the battery backups that are commonly available in data center computers and simply flush the data out to disk on a power loss event. And so you can notice that the backups are buffering updates, and over time they're writing them out to disk. And so we're forming a log structure on disk. But what's perhaps more interesting is we're actually forming a log structure in RAM as well. As these updates are coming into the master, we're appending them to the head of an in-memory log, and that log is simply being replicated across the cluster. So this gives us very fast space allocation on updates, but it means we need a log cleaner to reclaim space in the master's RAM, and just reclaim space on the disks on the backups. And that log cleaner is also helpful because it helps over time to combat fragmentation in the master's RAM. So the final thing that a master has is a hash table in its memory, which maps keys to their location in the in-memory log, which allows us to service read requests. So this is it. A master is very simple. It's simply a hash table, and in it, a bunch of objects concatenated in memory to form this log. So we want to recover quickly when we crash. One of these masters crashes. So what do we have left? Well, we have this log data stored on backups, but we need to get it back into RAM and reconstruct that hash table I described. And we want to do this for an entire host, say 64 gigabytes of RAM in just 1 to 2 seconds. So to do this, we're going to have to really leverage the scale of the cluster. If we don't, and say we store each of our backups, each of the backups stores the entirety of the log for the master on just these 3 backups, well, we only have 3 disks to read from during recovery, and it'll take 210 seconds to read 64 gigabytes back from those disks. Well, we have plenty of disks in the cluster. We just need to take advantage of them. We do this in RAMCloud by scattering our data out across the cluster. So the in-memory log I described is broken into 8 megabyte regions we call segments, and each of those segments is backed up on 3 different backups chosen randomly from the cluster. So this means over time the master is scattering its data across the backups, and that we can read from all the disks in parallel when a master crashes. So 64 gigabytes over the aggregate disk bandwidth of the cluster puts us back on track for the time frame we want to recover in. But we immediately run into a second problem, which is no single host can even pull all this data together. Even at 10 gigabits per second, it'll take 60 seconds to bring this data onto a single host. Even barring that, bringing it into memory and reconstructing the hash table will still take longer than our target time frame. But we have plenty of NICs and cores. We just need to divide our work up. So if we can split that work up 100 ways, we'll be back on track to recover quickly again. So we do this in RAMCloud using what we call partitions, which are simply subsets of objects from a master. So when a master crashes, instead of having a single host recover that contents of that master, we have just one partition recovered over several recovery masters. So each is just recovering a subset of the objects. And one nice property about this is it also means that we don't need an entirely idle host standing by to recover another host. We simply task normal masters with incorporating this data from the crash partition into their normal workload. So here's how partitioning works a little more explicitly. During a crash event, each of the backups receives a notification from the coordinator that a particular master has crashed. And the backup knows which segments it's stored for each master. So it begins to load those segments from disk, anticipating that the recovery master will be asking for that data shortly. And along with that, the coordinator sends a little map describing which partitions will be involved in which key ranges they're going to be recovering. And so the backups, as they're loading these segments, begin skimming through these segments, looking at each of the log entries, and determining which keys they map to, and then bucketing them according to the partitions that will be involved in recovery. So this means that each of the recovery masters, when they ask the backup for data, only get the log entries that are relevant for their recovery. So this means that we've divided the work well across the many disks, the NICs, and cores of the cluster. So this puts us in a good position to recover quickly. Now, in some sense, this is kind of a distributed parallel job, much like MapReduce applications, except for here we're even more sensitive to stragglers than the traditional problem is, because we have this very tight time budget of 1 to 2 seconds. So it's important in RAMCloud, while we do this parallel work, that we divide work very evenly across our cluster in order to recover quickly. And also, since the system's intended to scale, we have to avoid centralized bottlenecks, which means in RAMCloud during recovery, nodes often have to work without global knowledge of what's really going on in the rest of the cluster, instead of relying on local decision-making techniques. So one of the most important challenges we had to solve was balancing the amount of time each recovery master took to recover as a partition during recovery. If we gave any single recovery master too much data or too many objects, it would either take too long to get the data back or to reconstruct its hash table, and recovery would be slow. So in RAMCloud, we have a structure on each master called a profiler, which is being actively updated online as object updates are coming in, which is tracking the density of the key ranges inside the host, both in terms of the number of objects and the amount of data stored inside them. So then when a master dies, we can efficiently divide up its resources amongst, its work amongst the recovery masters. And another form of scattering, or another form of balancing I've already talked about, is this segment scattering. But if we put too many log segments on a single backup during recovery, it will take a long time to load that data back from disk, and recovery will be slow. So we use an approach similar to Mitzenmacher's power of two choices here. Basically, the master during normal operation, as it's placing its segments, chooses a candidate set of backups from amongst the cluster, and knowing where it's already placed its segments and using a small benchmark provided by the backups, it can get an estimate of the amount of time it thinks each of the backups will take to load its data during recovery. And basically, it's optimizing to minimize the worst case disk read time during a recovery. One interesting problem in RAMCloud is if there's some catastrophic failure, we need to be able to tell the user that we've lost data. So if we lose all of the replicas for one segment, it's not actually easy to tell. And that's because in RAMCloud, there are many, many logs. There's a log for every single host in the system. And so because hosts are allocating many thousands of segments per second and their cleaners are freeing many thousands of segments per second, it's impossible to essentially track at any given moment which log segments belong to which logs. So instead, masters are recording a catalog of segments, log segments into their own log, and then the coordinator can find this during recovery. And there's a bit of a trick there in making sure that we can find the most recent log segment in cases that we've lost the copies of it, or detecting when we've lost all the copies of the most recent log segment. But I'll let you see the paper if you're interested in that. So we have a small cluster with 60 machines that we run our experiments on. Each machine had 2 disks that delivers 100 megabytes per second. They're connected up with InfiniBand NICs that are limited by our PCI Express bandwidth and are hosted 25 gigabits per second. And then we connect it all together with InfiniBand switches and a 2-layer topology, providing us with very nearly full bisection bandwidth. And we're using this as an approximation for what we believe data center networks will provide in 3 to 5 years, particularly with respect to latencies. So before we can run a recovery, we first need to know how much data can a single recovery master recover in just 1 second. Well, for this, we plotted a recovery time on y-axis, and we fed the system larger and larger partitions of data to see how long it would take to recover on a single recovery master. So on the x-axis is the amount of data we're feeding it. And we gave it virtually unlimited disk bandwidth, so this is completely a measure of the bottleneck on the recovery masters. So along the 1 second line, you can see we can recover 400 to 800 megabytes per second, depending on the size of the objects in the log. So for the rest of the experiments, we'll try to recover 600 megabytes per host, which should be comfortably recoverable in about 1 second. So the most important question we wanted to ask with our evaluation is how well does recovery scale? Well, we have only a 60-node cluster. So what we did is we started out with a very small experiment and kept adding more hosts and data to it to see if our recovery time stayed constant. So here's how it works. We started with a master and we loaded it down with 600 megabytes of data, which is scattered across 6 backups in the cluster. And then we crashed it and recovered it to 1 host. Since we're scattering data across 6 backups, the 6 backups should be able to read that data in about 1 second, and the recovery master should be able to replay that data in 1 second. So if this all happens in parallel, we're hoping this will happen in about 1 second. So next, we doubled the amount of data on the crash master, doubled the number of backups, and doubled the number of recovery masters. And still here, we have 1,200 megabytes of disk bandwidth, 1,200 megabytes worth of bandwidth recovering the data. So we're hoping this will still stay about the same amount of time as the prior experiment. So we kept incrementally scaling the same experiment until the point where we get 12,000 megabytes, or 11.7 gigabytes, stored on a single master that we crash, which is scattered on 120 backups being recovered to 20 recovery masters in our cluster. And so this is the results. Recovery time on the y-axis, number of recovery masters involved on the x-axis. So you can see for 1 recovery master, we're recovering 600 megabytes in 0.95 seconds, and it only takes 1.1 seconds to recover 20 recovery masters, bringing back 11.7 gigabytes. So it's relatively flat, and what's really important here is that at 100 recovery masters, we're actually recovering an entire host's worth of RAM. So if we had a large enough cluster, it looks like we'd make our 2-second time budget. And then as for the slope, it turns out that there's this blue line just underneath the red line, which it's tightly tracking. And it's the reason that this blue line is basically measuring disk stragglers. So whichever disk is taking the longest time during recovery is basically the thing that's forcing this line up slowly. And the reason that it's going up is because as you add more and more hosts to recovery, the probability that a disk is slow gets higher. So next, we wanted to make sure that our software scaled well, but we only had this small cluster and we were limited by disk bandwidth. So at this point, we swapped out all of our disks for SSDs. So we repeated the same experiment, but instead of giving six disk-based backups to each recovery master for bandwidth, we instead scaled with two 270 megabytes per second SSDs per recovery master. So we're not quite tripling the disk bandwidth there, but this allowed us to triple the amount of data we're recovering and basically involve every host in our cluster recovering 600 megabytes apiece. And the end story is that we were able to recover 35 gigabytes of crash host data in 1.6 seconds. And at this point, we're more than halfway to recovering an entire crash host RAM, which is great. So it looks like even with a cluster maybe twice the size of what we have right now, we might be able to recover entire hosts. So one last analysis we did was the probability of data loss on a year versus the amount or the number of hosts our system scatters data across. As you add more and more servers to your cluster, you're scattering your data across more and more, and the probability that multiple simultaneous failures can cause data loss starts to go up. So there are some important assumptions on this graph. First, we're assuming 2 failures per year. The failures are independent, and that each failure loses the entirety of the contents of both RAM and disk. And finally, that we're using a replication factor of 3 here. So you can see down here, RAMCloud is at the bottom. With its 1 second recovery time, it looks quite durable. Even scaling out to 100,000 nodes, the probability of data loss in a year is pretty low. What's interesting is this is actually a different configuration of RAMCloud. Generally, we run with 3 copies on disk, and all the experiments I showed are 3 copies on disk. But even with just 2 copies on disk, it does quite well. So what's interesting next is the blue line above the red line. As you go from 1 second recovery times to 10 second recovery times, you see from a factor of 10 increase in recovery time, you see more than a factor of 100 increase in the probability of data loss in a year. So it turns out that our fast recovery actually dramatically helps our durability story. So then one last important point about this graph is if you look at the green line, for a host that scatters, or for a system that scatters data out in triplicate across the cluster and has recoveries on the order of 100 seconds, the probability of data loss in a year as you reach a scale of 100,000 hosts or so is reaching over 10%. And it's interesting because this corresponds to systems like GFS. So a system like GFS, which triplicates its data, may either need to go to 4 copies on disk to achieve a scale of 100,000 hosts or so, or simply needs to limit its cluster size to ensure durability. There's a lot of related work for RAMCloud, and you can see the paper for more. Clearly, the log structured file system has an impact. Each of them stores its data on disk in a log structure with this segment style. One difference is RAMCloud has this in-memory copy of its log. So this allows it to have a more efficient log cleaning strategy because in LFS, segments had to be read from disk and live objects had to be recopied out to the disk. In RAMCloud, we never have to read except for during recovery. We simply copy the objects to the head of the log in memory and then re-replicate the objects. People often ask us about memcache. Memcache is another key value store that works out of memory, but it's a cache rather than a persistent store, so applications have to explicitly fetch objects from the backing store them in cache, perform shoot downs on object updates, and all that. And also, applications' backing stores are often orders of magnitude slower than the cache itself. And so this means with any substantial fraction of cache misses, that applications have a hard time reasoning about the performance they can expect from their cluster because the cache misses can add up to a relatively uneven performance from the cluster. And finally, when hosts crash in memcache clusters, they're usually refilled on the backs of these cache misses, which can take hours or days, during which performance is degraded, whereas RAMCloud can recover in just a few seconds. And finally, Bigtable is a system that's similar to RAMCloud in a lot of ways. It's primarily a disk-based storage system, but it scatters its data using GFS as a backing store, and then logs on top of this in a similar way that we do. One thing they do is they actually explicitly store their index on disk, which eliminates the need we have for replaying our hash, to reconstruct our hash table during recovery. So in conclusion, RAMCloud is a system that uses disks for durability that are quite cheap, but still retains RAM-like performance by limiting synchronous writes from the update path. And our system, because it uses disks, needs this fast crash recovery system to restore availability and performance to the cluster, which we think we can do in 1 to 2 seconds at scale for entire crash hosts RAM. So right now, with our small test cluster, we can recover 35 gigabytes of data in just 1.6 seconds. And to do that, we have to spread work out across the entire cluster. We think that RAMCloud has the potential to really bring RAM-based performance to a number of applications. In particular, we think it's important because it allows access to large-scale data at latencies that are 2 to 3 orders of magnitude better than what we're seeing today. And it's still easy to use because it's durable and available. So we think this has the potential to enable application developers to bring a lot of new features to their users and to create more interesting and more data-intensive applications than ever before. So with that, I'll take questions.
Hello. Meysam Yavande from Yahoo Research. One purpose of replication is to improve scalability for read operations. The more copy of data you have, the more you can split your read workload over the copies. So I'm wondering what happens to hotspots.
Absolutely.
Yeah.
It's a great question. So we've got this brazen approach that we don't really believe we need replication for performance at all. We might be wrong about that, but right now our server can deliver just about 1 million requests per server per second, and we're not really sure that there are objects that need more than 1 million requests per server per second. I think if you were hitting that point anyways, hopefully that'd be a relatively immutable data object that you might be able to store like locally in memory in your data center application. So I think at the end of the day, it'd be kind of hard to believe that, well, we'll see, but so that's the idea. Basically, don't replicate, we're just fast as possible.
Marcus Aguilar, Microsoft Research. So it seems the main technique that you're using here, which is to scatter the backup, actually creates a trade-off, which is that if you need to recover lots of machines, let's say all of the machines, when you have a power failure, for example, you have to pay an extra overhead because you have all these messages flying left and right in your network to recover all of those. And I was wondering if you have additional techniques to recover fast in that case. For example, perhaps writing to the local disk of each machine in addition to writing to the scatter log or something else.
Right, that's a great point. So, so what do we do for cold start? What happens when all the data is gone? So we're actually kind of in the middle of designing and implementing that, which is kind of weird that we're doing it after this part, which seems more complicated. But I think at the end of the day, what you're going to end up saving there is basically network bandwidth during that recovery time. At the end of the day, we have plenty of network bandwidth, so it's okay to basically kind of unscatter all this stuff and restore it onto individual hosts. The network's not going to be the thing slowing you down there. It's just going to simply be the fact that you only have so much disk bandwidth with which to bring all these hosts back. So we could do something like store things locally. The problem with storing data on local disks is then you're kind of limiting yourself to the disk bandwidth for writes on that particular host. We buffer these updates. And it turns out the way when we scatter, we can actually buffer data in the memory of one set of backups and then the next set of backups as you keep it pending the header log. So we actually have burst bandwidth that can exceed the speed of disks for very long periods of time in RAMCloud. We'd like to keep that property, so that's another answer.
Hi, Joel Nider, Qualcomm Israel. Your recovery looks very impressive. But my question is actually about writing. You mentioned that you have to use synchronous writes to the disk, and I wasn't clear on why you can't use asynchronous writes.
So we are effectively using asynchronous. I see what you're saying. That's effectively what we're doing. Basically, we are delaying the synchronous write until we can do it in the background and kind of offline. So we're basically just buffering the updates in RAM until there's a more convenient time off the fast path to write this data out.
So it is asynchronous.
Yeah, it's asynchronous, right. So we're considering things durable once they are in enough hosts other RAMs. So yeah, that's how it works.
Okay, thanks.
Marvin Timer, Amazon. So if you do that, what happens during a power failure? And what is the implication about data loss?
So, right. So that's a problem. It turns out that the other systems actually have the same problem as well. Things like Bigtable, for example, will write data out to GFS, but GFS actually just pushes this into the OS buffer cache, and you have to basically hope the OS does a good job pushing this data out in the case of power failure or something. So right now, I kind of gave the answer of you can count on battery-based backups in the data center. Those have we've gotten varying reports on the reliability of that approach. You can also do things like use non-volatile RAID controllers. And there's some other kind of more experimental things going on these days with things like flash-backed RAM with supercapacitors. So when the power goes out, you basically would store your data only in a set of piece of DRAM that can be basically fast copied out to flash in the case of a power failure using a supercapacitor. So there's some things we can do there. But at the end of the day, I think we're no better off than any other data center storage system, which is trying to avoid synchronous disk writes in that regard.
Hi, George Porter, UC San Diego. This is great work, by the way. One question I had was, a couple times you mentioned both low latency data center interconnect, but also a data center interconnect that's very homogeneous in terms of the bandwidth it delivers. How dependent is your system on that homogeneity assumption, both in normal time operation and also during recovery?
So that's a great question. So we basically designed this system from the ground up, relying fully on the fact that we would have full bisection bandwidth in future data center networks. That's probably a reasonably controversial thing to, so we're kind of counting on it. I think there are a lot of things we can do. I think during normal operation, there aren't any major problems. It's generally during recovery where there's this huge cross-section of bandwidth you're using. In the end, what it would probably mean is you would, if you didn't have full bisection bandwidth, you want to come up with some form of locality for backups. You want to scatter your data out broadly enough so that there are plenty of backups which to scatter, but at the same time, you'd have to localize so that you're not going across whatever switch it is you're trying to avoid that's a bottleneck. And we've talked about this a bit here and there in design meetings. I think it's fully possible to do, but until we have a need for it, we won't worry about it. Right now, we're able to achieve full bisection bandwidth using our small 2 racks. So,
Jin Chen from Fudan University. In the paper, you mentioned the server response write request from client only after the acknowledge of the back server is arrived. Okay.
Mm-hmm.
So I think the write throughput is limited by the bandwidth of the network, and at the same time the process time of the backup server. So what about your throughput of the normal execution? How did you compare with the memory cache D, and the router or switch in the network will be the bottleneck of your system's normal execution?
Okay, so you're asking about basically you're essentially asking what's our write performance like and what's it limited by, right? So at the end of the day, we are limited by disk performance eventually. As I mentioned a little bit in an earlier question, we can actually buffer up data in many backups RAM. So if a single host is seeing high burst bandwidth, it can actually be buffering segments on many, so it can begin buffering segments on many backups. So you can actually exceed the disk bandwidth for quite a bit of time until you've used up enough buffer space that it gets sketchy to keep too much in RAM in case of a power loss event. But yeah, so we do take 2 round trips, basically. It's about 2 round trip time RPs for a write request, essentially, because 1 comes in, you send 3 out, and then you wait for the response to come back. So right now we're seeing something like, I think I measured it right before we came here, I think I was looking at 14 microseconds round trip time for a 100-byte write request. Right, I think it's a good question. You are kind of, you're taking, your network bandwidth kind of goes down by 1/3 because we're triplicating the object on outbound from the NIC on the master, but with 10 gigabit Ethernet, that's actually still several hundred megabytes per second that we can sustain on a single host. So I think in the end, the disk bandwidth bottleneck actually eventually would be the thing that would be the more limiting factor there, but they're kind of close together, I guess, with SSDs. But
So it's in Princeton. So I thought you guys did a really cool job of taking away the disk bottleneck by really leveraging the size of your cluster. But assuming that network bandwidth is now the bottleneck in your system, does that mean that in its current state, the performance of recovery will be proportional to how good your NICs are? Let's say if you didn't have the InfiniBand NICs you're using now and you just had regular NICs.
Right. Okay, so that's a great question, actually. In particular, we've got 25 gigabits per second, not 10 gigabits per second, so that's quite a bump. So the answer to that is it's not really a big deal. It just means you have to scatter your recovery out a little more broadly. So it turns out that with 10 gigabit, if we would have had a 10 gigabit network, we'd have to recover something more like 300 megabyte partitions instead of 600 megabyte partitions. Particularly, the problem is basically re-replicating the log contents during recovery causes kind of a threefold explosion of data coming out of the recovery master. And so, yeah.
Okay, thanks.
Alex Nguyen from UC San Diego. So I'm trying to wrap my head around your model, and if I think I understood you correctly, basically when you have a failure, you're proposing to take the entire capacity of your data center and focus it at restoring that one, one server. So from a usability point of view, you have a pause in the availability
exactly
of the data center.
Yep.
Okay. So as you scale the data center, you showed us those ominous graphs. You're going to start to have failures. Right?
Absolutely, that's right.
So I'm just wondering, what does it mean for the availability of your obviously, your recovery times are going to decrease as well at scale. But so I'm just trying to get my head around the model. So basically, you're going to have a data center that's going to be on-off with some periodicity based on your failures. I'm just wondering how you see that playing out.
I think that's true to some degree, too. And we've talked about this somewhat. One possibility is to somehow limit recovery to some degree and try to proceed with normal operation in the meantime. Particularly if you have 100,000 servers and only one of them's down, you would be able to like to access the other ones in the meantime. On the other hand, it depends on your application. So if your application is really very data intensive and just all of your servers are talking to all of your storage servers, you're going to end up talking to that storage server and asking it for some data anyways, the one that's not available. So in some sense, even though you're taking pauses that kind of affect the other, you're kind of affecting the performance of the other nodes by doing this very aggressive recovery strategy. It's kind of better just to get that data back online and start servicing requests again, because if an application really is taking advantage of a lot of the hosts in the system, there's a good chance they're going to get stuck waiting for that other host anyways, and it'd be better just to get everything back online. So,
okay, one follow-up. Do you understand how recovery from multiple simultaneous failures scales? Because it seems like as you get larger, the chance of simultaneous failures will also increase on you. So if you had to recover 2 servers at once or 3 servers.
Right. So we haven't actually done multiple simultaneous failures yet. I think that'll probably be one of the next things I start working on in the next couple of years or so. But I think at the end of the day, I think we can recover from multiple simultaneous failures much in the same way as one, but you end up with, you're right, because it's a very, very resource-intensive thing, and so it's going to be a tough balance between normal operation and how do I balance that between like these 2 or 3 or whatever ongoing recovery. So that's going to be a really tricky issue.